Hello students, we are going to learn today what are computable Turing machines. If you have heard the earlier lectures, you might have learned the introductory part on Turing machine, how Turing machines work as language acceptors, and few examples on designing Turing machines. The next part of Turing machine that we are going to learn today is computable Turing machine. If you remember in the previous lectures, I had said that Turing machines can produce some output for the given input. Just imagine, have you ever drawn a DFA for addition of two numbers, for computing the average of numbers, for copying a string, for finding out the square root of a number? Have you ever designed a PDA for such kind of purposes? Have you ever designed a DFA or a PDA which can compute n mod 2, that is find out the remainder when you divide by a number? If you recall, we haven't done this. The reason is those machines didn't have enough memory and were not capable of computing such things. But today, as I've already said, the most powerful machine, yes, the Turing machine, is also capable of computing something. Hence the name computable Turing machines. The earlier examples that we learned, where the only aim of the machine was it had some input and it just told us whether that input string is accepted or whether it is rejected. But today, the computable Turing machines will not give you the answer in terms of accepted or rejected, but rather it will tell you whether the output produced is there onto the tape. That means you are supposed to provide the input data onto the tape. The Turing machine will process the data on the tape and directly will write the output onto the tape and simply halt. So you can say there is nothing called as halt with acceptance and rejection, but rather simply halt. So let's move ahead. So you can see here. So computing something is just computing a function. So f of w. So what does that mean? W is an input and f is the function that you apply on w. For example, f of w can be a string w and the function f finds the reverse of the string w. So let's assume the string is a double b. So what did I say? The string is a double b. So the string is a b b. And if you apply this function f on this string a double b, as I said, what is a function f? Reversing a string. So what will be the output onto the tape? It will be b, b, and a. So yes, this is what is the concept of computable Turing machine. So right now, you can see in this diagram something called as domain, which is D. And remember, the string W should belong to the domain D. Right now in this example, what was my string? A double B. So it was a simple string made up of A's and B's. So right now the domain for me is the sigma closure, the universal set, which is made up of all the strings, which is a combination of only A's or B's or both A's and B's. So rather I would say A or B bracket closure is going to be my domain. Now, no wonder, as I said, these Turing machines can also operate on or compute strings as well as they can compute numbers. They can do addition, subtraction, multiplication, division. You just imagine of some computations, and yes, the Turing machines are capable of doing it. The only thing is we have to decide the strategy. So let's assume now, let's take an example of, we take a number, say let's take it as f of 3, and this function f is supposed to compute the square of 3. So yes, what is the square of 3? Yes, it's 9. So answer you find on the tape is supposed to be 9. So this is how the computable Turing machines we are supposed to learn. So they work both with strings as well as with integer numbers. The next what we are going to learn is the concept of what I said, domain and the result region. Now if you look at the domain D, now I said if the example is on computing the addition of two numbers, and the domain for us is the set of natural numbers. See, what's the domain? The set of natural numbers. If you just take any two natural numbers and add it, the result is again a natural number, so there's no problem at all. But if you take the f of w as two natural numbers and you're going to compute the subtraction of two numbers. So let's take the number as 5 and 3. So 5 minus 3 is going to give you what? 2. So yes, the output in this case is going to be 2, which can be easily represented on a tape. But if you have the numbers as 10 and the other number is say 15, and if you now subtract 10 minus 15, the result is minus 5. But the problem is minus 5 does not belong to the set of natural numbers. Hence, we have to take care that the input and the output belong to the domain that we have selected. So that is very, very important. Hence, if you will, when we move ahead, you will find that it is called as computing a partial function with Turing machine. Why partial? Because you are restricted to the set of natural numbers, or it could be whole, or whatever the domain that you have selected. Since it's restricted to your domain, we call it as a partial function. So computing a partial function with a Turing machine. Okay, the next what we learn here is, you can see here, you provide the input, the Turing machine works, and you get the output. Let's go through an example for addition of two numbers. Do you know how these small children learn? Okay, just imagine in front of your eyes the number 5, and now you have a number 3. So if I ask you to count how many fingers are these, you will say in all they are 8. So that's how you simply do the addition. That's exactly how your Turing machine works. Now, the very first question is, how do you represent the numbers onto a tape? Just remember, how do you teach a child in a nursery or in first standard to count? Suppose if you want the student or the child to know what is 5, do you symbolically represent simply what is 5? No, the child won't understand. But you draw 1, 2, 3, 4 and 5 pencils or 5 birds or 5 boxes, and if you ask the child to count it, now this becomes actually the count 5 or the magnitude 5. This is what exactly we are going to do. Strings like made up of zeros, ones or A's and B's can be easily written onto the tape. But when it comes to integer numbers, we are going to use either ones, or you can also use successive 5 zeros to represent the number 5. So successive 5 zeros can be represented or can be considered as 5, or you can go with this. Any one of the possibilities or the methods we can use. So remember, strings can be easily written onto the tape. There's no problem at all. But when it comes to integers, how are we going to represent integers onto the tape? By using either successive ones or successive zeros. The next thing that we will look here is the, yes, as I said, this is the decimal 5, and you can see this binary equivalent 101. But if you look at this unary representation of the number, which is very easy for a Turing machine to manipulate, is 1, 1, 1, 1, 1. So it's 5 ones, which makes 5. So naturally, if you want to represent 5050, you should draw successive 50 ones onto the tape. Now look at this. A function f is computable if there is a Turing machine M such that you have this input, which is the original or the initial configuration. At that moment, the machine is in which state? Yes, it is in the initial state. The tape head is pointed at the beginning of the string, and gradually the machine will start reading the entire string. And after it finishes, you can see here the answer, that is f of w, is present on the entire tape, whereas you can land into the halt state. That can be called as an acceptance or may not called, but stopping the machine or halting the machine is very, very important after you finish the computation. So how do you represent the x and y, or a function made up of two parameters? Remember, you have learned in C, C++, or in various programming languages that you can have functions with no parameters, one parameters, two, three, or you can say arguments. Now here we have a very first example, which is for addition of two numbers. So I'm talking of two. So here how many parameters or arguments do you have? Two. So exactly remember, the input data to the function can be multiple parameters. All these parameters or arguments have to be stored onto the tape. Now the question is, if you imagine two numbers, let's say if the number is 3 and 2. So how do we represent 3? It's 1, 1, 1. And how do we represent 2? The number 2 will be represented as 1, 1. And we want to add these and get the result as, yes, the result we want is 5. Now, the problem is, if you take the tape and if you represent it with 1, 1, 1, 1, 1, you directly get the answer. But it's not the case. This is a separate argument and this is the separate argument. In order to recognize or distinguish between the two arguments, we need a separator or a delimiter, and in this case we are going to use a 0 as a delimiter. So you can see here x is the first number, you use 0 as a delimiter or a separator, and this is the second argument y, and this is your input that is stored onto the tape in this type. So now let's think of a strategy and check how we can get the final answer onto the tape. As I said, 5 and 3 together, if you count my fingers, it simply becomes, all fingers together becomes 8. Exactly in the same way here, if you simply just go on reading this once, and if you erase this 0 or replace this 0, okay, let's imagine that we have the blanks before and at the end of all the list of arguments. What you have to simply do is start reading the string from left, go towards right, go towards right. In between, you can convert this 0 into 1, and then finally go to the extreme right end, move one position towards left, and convert this 1 into a blank. I repeat again, you had 1, 1, 1, a 0 in between, and 2 ones at the end. And these all arguments are enclosed between two blanks. What did I say the strategy is? This 0 will be simply converted into 1. And this last one will be simply converted into a blank. Now, if you count these ones, they are 1, 2, 3, 4, and 5. And yes, the answer is there onto the tape. I hope you have understood this. Let's check it into the diagram. So here it is. The initial state, series of ones, a 0, which is a separator, and again all the series of ones, and a blank. I said it is included in the blank at the extreme ends, the leftmost end and the rightmost end, and all the arguments are between these two blanks. Suppose if I use a blank here in between as a delimiter or a separator, the problem is you will then not know which arguments or how many arguments belong to your function. Hence, it's better to use a different symbol to distinguish or to separate the arguments belong to the same function. So hence we have chosen 0 here. You can see the answer. Now you have successive series of ones, and the last one has been converted into 0. Or the strategy what I discussed was, in this the last one can be converted into a blank, which is also correct. So you can have multiple strategies or different strategies for the same problem. Okay, let's see how the machine has been designed. So you can see here what we have done is start reading from the left, keep on reading all those ones, and keep on moving towards right and right and right till you come across that 0 in between the two arguments. What did I say? This 0 will be converted into 1 and keep on moving towards right. Keep on reading the remaining ones and reach the extreme right end. Keep that blank as it is and move towards left. And the extreme last one or the rightmost one either can be converted into a blank or can be converted into a 0, and you can keep on moving towards left. Now you will find these all ones onto the tape. Simply keep on reading them, keep on moving towards left till you come across a leftmost end of your string, which can be recognized by this blank, and just land into the halt state. That means you have finished the computation, or rather the machine has finished the computation and the result is onto the tape. So here you can see 1 1 is the number 2, again added with 1 1 the second argument 2. So 1 1 plus 1 1, the result seen is 1 2 3 and 4 successive ones. Let's see another example where we compute 2x. So if you give the number as 3 into 2, what you should have onto the tape is 6. So it's as good as you have 3 ones onto the tape. So it's something like this: 1 1 1. That's a single argument, a function with a single argument, and the remaining of the tape is full of blanks, all successive blanks. So we are here. Keep this blank as it is, move ahead. Now we want to copy this entire string here so that it gets doubled. So let's start. First, let us convert this 1 into x, and corresponding this blank will be converted, or we can do one thing. We can convert all these ones into dollars. So we convert all these ones into dollars, and then we come across a blank. Now we read the first dollar, convert it back to 1, and go to the first blank and write 1. Again go back to the next dollar, again rewrite it as 1, and corresponding blank will be converted into 1. Again this dollar will be converted into 1, and again this blank will be converted into 1. So you check, what is this? It is 6. So 3 into 2, we get 6, and the answer is onto the tape. Isn't it simple? So repeat again, what did we do? We converted all those initial ones into some different symbol. You can choose X, you can choose Y's, you can choose dollar, whichever is comfortable or whichever you like. And accordingly, one by one, you can later on convert those. So for example, if I choose X, I convert this into X, this into X, this into X. And when I reach a blank, I know that I have converted all the ones into X. Now, let us move back. What did I say? We will again do the reverse. We will convert this X into 1 and write corresponding 1 at the end here. That is, blank will be replaced with 1. Again convert this X into 1 and write 1 1 here. Convert this X into 1 and write another X here. Now here we have 1 1 1 1 1 1. So we have 6 ones and the answer is present. So I hope you have all understood the strategy. Let's now check how the machine can be drawn.